All right, welcome back, everyone. Questions on the homework? I heard some murmurs. So I will not be having office hours tomorrow. Unfortunately, I've got an all-day meeting. So what I can do, Jermaine, if this is okay with you, I'll have the homework due at 5 on Wednesday, so that gives everyone a chance to meet with you in the office hours right after class on Wednesday, because I'll be completely unavailable all day tomorrow. So if that works. Yes, question?
Yeah, on the one where you asked to find the binodal and spinodal points,
Yeah.
I think I understand that spinodal is a second derivative of Gibbs free energy.
Mm-hmm. Where it equals 0.
Yeah,
that's the
where it equals
inflection
0.
point of the Gibbs free energy, where it goes from stable fluid to unstable fluid.
But for the binodal points, that's when it's less than 0, or
No, the binodal is when you satisfy the liquid-liquid equilibrium criteria.
So potentials are equal, or
The partial fugacities are equal. So for the spinodal, this one's actually easier to do. You'll get a nice analytical expression. So you'll get the second derivative of the Gibbs with respect to composition is equal to 0. That's the definition for where your spinodal is located.
Mhm.
And you'll have to know, of course, like there's when you have your Gibbs free energy, it'll look like this for a two system liquid-liquid phase separation, where you have two local minimums, right? So these are going to be stable, stable, and then this is going to be the unstable region. So the spinodal is going to be the region bound by this. So this means that this is going to have to be the region bound by, that's negative, so let's be less than 0. More specifically, that's a better way to think about it.
okay.
But you'll be solving for the 0 points where it transitions from a stable to an unstable fluid. Now the binodal, this is where you have your phase coexistence region. So this is going to be where this expression is satisfied here. Now, in a system where you have it defined kind of like this, and it's a nice, simple, really straightforward activity coefficient model, you could think of it, these are the minimums of the first derivative, but that's probably not the best generalized way to think about it. Because if you're dealing with a generalized software, for example, like Aspen or Promax or some other fluid phase simulator, it's not necessarily going to want to assume, it's going to want to have a global reference condition for all the calculations it performs. So if you're mixing two things together, it's not necessarily going to reset its global reference condition to be the temperature and pressure where you're mixing the two things. Right? So in this case here, I've drawn so that the Gibbs of pure 2 and the Gibbs of pure 1 are both equal to 0. That's not necessarily going to be the case with generalizable code, because that's going to be a lot of, if this is this, then that is this, right? So it's going to be a lot more complicated. So in general, what you'll see is you'll have conditions like this where you'll have pure Gibbs 2, pure Gibbs 1, and these are going to be calculated from absolute reference conditions that the software sets up, or maybe something that's user definable in the case of using it. So then the curves might look more like this, in which case it's not the minimum. The solution actually ends up being the tangent.
Yeah, you would have to be given the information, the Gibbs of the pure species, right? In order to plot a curve like that.
If I were to take this and kind of flatten out both ends, it should look like this.
By just saying that both of them are equal to 0.
Yeah, so this is an exercise that I'm not expecting anyone to do, but if you took this Gibbs right here and then you added a linear function to it, the minimum positions should shift a little bit.
Okay, but for the binodal, if we have something like that with fugacities, that's that big equation that we're going to have to solve numerically, like in the earlier problem?
Well, by big, it's not terribly big for the one constant Margulis, right? So in this case here would be a. So this is going to be x1 phase 1 gamma 1 phase 1 equals x1 phase 2. That sound is going to drive me crazy. x1 phase 1, that's going to be like a exp of, oh no, I got this wrong. The a's inside here, right? a1 minus x1 phase 1 squared over RT, right? And then the mirror on the other side.
Mm-hmm.
So they're big, nasty. They're not nearly as bad as, for example, the partial fugacity coefficients, like if you're calculating from an equation of state.
But writing out that expression, that's what you're looking for
That's going to be the binodal solution, yes.
Okay.
That's going to be the best, most unbiased way to get to the binodal, is to solve that system right there. So you'll have two equations, two unknowns. If you do your substitution right, it should be two equations, two unknowns. If you don't do your substitutions, it'll be 4 and 4. Whereas two of the equations will be summation of xi phase 1 equals 1, summation of xi phase 2 equals 1. But those are readily substituted into your partial fugacity expressions and your activity coefficient models. All right. Let's move on. So the Sandler book is titled Statistical Thermodynamics, meaning that we don't consider kinetic processes, like looking at collision theory of gases or things like that, where we're looking at reactions occurring. We're only looking at the long-term equilibrium, but in general, the tenets of what we're talking about, you can more generally think of as statistical mechanics, as a sort of an overarching field, whereas statistical thermodynamics would be only looking at the end-limiting cases. So as we talked about on Friday, our goal here is we want to marry what we understand about macroscopic phase behavior and macroscopic properties to the concept and understanding of the molecular world. Right? If everything is built of atoms that are zipping around and behaving a certain set of rules, we need to find a way to relate between these two. But things can be very, very tricky. Right? 1 mole is 10 on the order of 10 to the 23 particles. I'm just going to truncate the other numbers here. So if I have, for example, a surface and a particle collides with the surface, we know that this is the molecular or atomistic underpinnings of what macroscopic concept? Pressure. So if we do this at a temperature of 300 Kelvin, which is very comfortable and well known to us, the energy associated with a single particle is going to be on the order of 10 to the, on the order of 10 to the minus 23 times on order of 10 to the 2. Now this is going to be equal to effectively kBT. Whereas the Boltzmann constant, as you recall, is just the ideal gas constant, but instead of per mole, it's per particle. So the kinetic gas constant and the Boltzmann constant is a proportionality relationship between the temperature and the energy of a particle. So that gives us, sorry, this is killing me, on the order of 10 to the minus 21 joules per collision, which is a very, very small number. But we have on the order of 10 to the 24 collisions per centimeter squared per second. So if we tie this all together, this gives us a finite pressure. Something that we can actually appreciate, that's on the order of magnitude of what we're accustomed to seeing. So yes, all atoms are very, 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 very small. And that was the chief criticism of Boltzmann's work when he first published it. But we also have lots and lots and lots and lots and lots of particles, so it ends up working out just fine. So in an ideal world, if we have time, I'll show some videos on YouTube highlighting this. What we had talked about is for simulations. Right now, so imagine particles are like NPC characters in a video game, for example. You want to give them a set of rules, they follow, they move around, and you just have, I don't know, a lot of them, and then all of a sudden you just call those particles We just call those characters atoms, and then we can see how they behave. So, let's see. You have collisions in real systems on the order of 10 to the minus 11 seconds. Times this by 10 to the 23 particles, and that results in approximately 10 to the 33 collisions per second for 1 mole. Right, so billion is, what is that? It's 10 to the 9, trillion is 10 to the 12, peta is 10 to the 15th. So this is a lot of collisions per second. So let's say, for example, we were to imagine our particles as moving around. I don't know, how many of you have seen kind of a video or have an understanding of what a molecular simulation looks like? Okay, so it'll be good to show the video later on. So in your mind right now, just imagine you have a box with particles kind of zipping around. Right, and then they bounce off each other, they bounce off the walls. Typically you don't have walls, you do what they call periodic boundary conditions. So if a particle flies out here, it flies right back in there. It's a clever way to make the system seem bigger. Now, but let's say, imagine we have rules of how every particle interacts with every other single particle in the system. There is no way conceivably that we could ever come close to simulating a mole's worth of behavior over the course of a second. So instead, we have approximately, in a standard computer simulation, right? And then of course there's people who push the envelopes in either direction. You have an order of about 10,000 to 1,000,000 particles. And that's a pretty standard fare. You can even get away with a little bit smaller here depending on the properties that you're trying to measure. So if I have 10,000 to 1,000,000 of these particles zipping around in a particular box, the time scale that I can simulate on a reasonable level machine or a reasonable level supercomputer or cluster node like we have at University of Utah is going to be about approximately picoseconds. This is pretty standard. Now if I've got a good workstation computer, you could probably get this done overnight or over a couple of days if you run for a couple of picoseconds. Right? Picosecond is
minus
10 to the minus 12, yeah, seconds. On the order of nanoseconds, right, a nanosecond is going to be 10 to the minus 9 seconds. So if you want a couple nanosecond simulation, you can do it. That's a pretty standard approach, but you need kind of a dedicated computer cluster to do that. So instead of having a lab filled with equipment, you have a lab filled with computers, and they're running 24/7 crunching numbers for you all the time. So on a reasonably sized cluster, a couple of nanosecond simulation, depending on how big it was going to take you, would probably take a couple of days, maybe a couple of weeks of simulation time. But that's fine if you have lots of computers. You can just set it up to go and go and go and go and go, and then as the results come in, the students analyze the results. Now, if you want to do microseconds, right? When I say research, I don't mean research simulating new compounds. I mean research kind of pushing the envelopes of what simulations can accomplish. Right? And this is where you need supercomputers. Right? In microsecond, again, it's going to be 10 to the minus 6 seconds. So if I'm trying to simulate a real process that occurs over the course of maybe minutes, let's say like a chemical reaction, I can't. It is not possible. So people employ lots of different simulation tricks with all of their basis in statistical mechanics. So for example, if I want to simulate a chemical reaction using molecular simulations, I can't do it at 100 degrees or 300 degrees Kelvin. I have to do it at 3 million degrees Kelvin to simulate what the situation would be like if I extended the time for very long, and then use an Arrhenius expression to kind of compact it back down again. So if you wanted to do microsecond-length simulations to study phase transitions, nucleation processes, chemical reaction, deposition, any sort of advanced kind of protein interactions, you would have to rely on the supercomputer that you would have to apply to time, have access to time to. So Oak Ridge National Lab has a supercomputer. I think it's called like the Cray Kraken or something. I don't remember the word, isn't it? Some based on some, I think, Greek monster or something like that. But as I mentioned in class the other day, we're pushing the limits here. So 122 petaflops is the fastest supercomputer right now. So this is the top 500 supercomputer. Top 500, I think it's cheating a little bit because it's a distributed cluster network. So it's not actually one computer in one spot. But this is 122 petaflops. FLOPS. This stands for floating point operations per second is a flop. So this is 122 times 10 to the 15 flops. Now, one particle doesn't equal one flop, right? If I want to do a picosecond simulation, my time step is going to be in the order of femtoseconds, 10 to the minus 15, to get good numerical accuracy of how these particles come close together. So as we can see here, for 1 mole, 10 to the 33 collisions per second, we can calculate, let's just say, for example, a really rough back-of-the-envelope calculation, we can bust out 10 to the 15 flops. Let's say one flop is one particle that you can characterize. That's still, we're missing a gap of 10 to the, I don't know, geez, what is this? 10 to the 18 seconds? What is that? It's a long, long, long time, right? Years, century, millennia. So no way we can come even close to doing it. So the problem is what we're going to do instead. So instead of simulating every single particle position every single time, which we can do for small systems, but remember this is back in the minds of 1910 over here, when we're working with atomic theory. So instead what we do, we apply the tenets of stat-mech. So the general procedure that I like to think of it as is we develop a finite simple system, something that we can kind of assess the rules of. Maybe this is a particle on a grid. Maybe this is a quantum mechanical particle in a box. Not something simple that we can actually analytically calculate or figure out. Right? We calculate the basic properties of a single particle in a box, or maybe the entropy of a particle on a grid. We play around with the math a little bit until we can develop a generalized expression, kind of similar to how we had to take the partial derivative of an infinite summation. Right? You have to work it out enough times so you can see the pattern emerging, and then you can find a way to generalize it based on the particle size. And then you take this expression and you scale it up to a size of a system that you care about, maybe an actual number of moles of a particle. And this is going to be the generalized procedure that we'll be talking about. So the first thing that we're going to be handling is a particle in a box, for the most part, because that's the simplest one. And if you apply this procedure to a particle in a box, non-interacting particles in a box, what do you think we're going to generate out of it? So what is a series of non-interacting particles in a box? Ideal gas. So if we take this approach to a single particle in a box, we should be generating the ideal gas. At least that's our goal. As it turns out, it works out well. Boltzmann had a good idea of how to solve these problems. Okay. We have to hammer out a few definitions to get ourselves in the mindset of the molecular world. But the key of this little introduction is that there's a lot of particles in the system. Okay. So what we're going to talk about is macrostates versus microstates. Now, we're only going to consider ourselves with classical systems, so we're not going to worry about quantum mechanics at all. So in strictly classical systems, a microstate consists of known values of particle velocities and particle positions. So if I know the position and the velocity of all the particles, and for this case here, let's think of it as a non-interacting system. So the energy of the system is just all the energy of all the individual particles put together. So what I mean by particle velocities is velocity of particle 1, velocity of particle 2, and so on and so forth. And same thing with positions. This is a position vector. So it's a position vector for 1, position vector for 2, so on and so forth. So a macrostate is going to be something like a collection of all of these properties. The internal energy, the pressure, the enthalpy, the Gibbs strand, if we don't lose too much again. So are atoms distinguishable or indistinguishable? I guess I need to clarify. If I have 2 helium atoms, can I tell the difference between those two? No. If I have a helium atom and a neon atom, can I tell the difference between those two?
Yes.
How can I tell the difference between those two? What was that?
The number of particles.
Number of protons. Maybe I could look at the spectroscopy measurements of it. I could try and measure the mass of it using a mass spectrometer. Right? So in general, the concept of distinguishability, so if I have a system of particles where I have velocity 1, velocity 2, velocity 3, so on and so forth, that is exactly equivalent to velocity 2, velocity 1, velocity 3, right? I can't tell these apart if they're the same atomic element or the same molecule. Now, if I have 2 different types of molecules, I can tell them apart. So let's say, for example, I have a partition, a box, and I have helium on one side and helium on the other side, and I remove that partition. Is any entropy being generated? Right? I'm mixing helium and helium. Is entropy being generated?
No.
No, because I can't tell the difference between the initial condition and the fully mixed condition. It's completely indistinguishable, so it's the same state. Now, if I have helium and neon on opposite sides of the partition and I open it up, do I have entropy being generated then?
Yes.
Right, because the helium would occupy the neon space and the neon would occupy the helium space, and that would have increased the entropy for both sides of those 2 chambers. So, indistinguishable, distinguishable. Now, going back, yes?
But in the first case, we can find helium on a place that it cannot see it before. I mean, it has more volume now.
If we can monitor one helium, and I say that that one helium now has more space, but I can't differentiate that helium on the left side of the compartment from any other heliums on the right side of the compartment. So in the case of distinguishability, they're indistinguishable. I wouldn't be able to tell if that helium had mixed or had already been mixed, or whatever the case would be.
But in this case, I have probabilities that all helium atoms will be on one side of the, but I cannot have this property before removing this kind.
So let me re-describe the system a little bit better. So if you had a compartment with a barrier in between, and you had an equilibrium distribution of particles on either side, so the same number of particles, the same pressure, the same temperature, the same density, then if I were to move this partition, I wouldn't be able to tell you if this was on side A versus side B. As soon as I remove the partition, there'd be no way of me knowing which particle was on which side of the partition when we started the experiment. But in the case of distinguishable, I would be able to tell if I contained this one with all helium and this one with all neon, I would be able to tell after I remove the partition that the neon is on the helium side. But in the case of it being indistinguishable, I would not be able to know which side it started on. So it's the same condition with the same state. So distinguishability, why do we have this? What's the quantum mechanical principle for why we have indistinguishability in terms of particles? Think way back when to your undergraduate quantum or physical chemistry course. Is there a principle that comes to anyone's mind? What's that?
Uncertainty.
Heisenberg uncertainty principle. That's where this origin is from. So in the Heisenberg uncertainty principle, we know that the uncertainty in the position multiplied by the uncertainty in the momentum, this is another way you can think of it as sort of the energy, has to be greater than or equal to Planck's constant. So this is plus minus in position. This one is plus minus in momentum, where momentum P is equal to the mass times by the velocity. And H is Planck's constant, which is equal to 6.63 times 10 to the minus 34 joule seconds. And this is the minimum quantized energy level. So you can never slice energy levels finer than Planck's constant. So likewise, that means there's also a minimum quantized position level as well. But it's very, very small that it's not important. Well, for us in the macro scale. So you can never differentiate between energy levels smaller than Planck's constant. I'm sorry, momentum has direction as well. So to illustrate this, if I start off with a box in time, and I have particles zipping around, and I call this particle 1, I call this particle 2, I call this particle 3, and I can freeze the snapshot. Ideally, right, just this drawing right here violates the Heisenberg uncertainty principle because I have a perfectly defined position and a perfectly defined momentum. Right, the momentum is basically the mass times the velocity pointing in particular direction. So this line represents momentum, and where I draw the dots represents the position. But then if I were to look at some time plus delta t, so effectively I have a variation in the momentum and I have a variation in the position. So then if I were to draw sometime again in the future, I would have no idea which of these two particles were in which locations. There is no amount of finely stepping the times to actually be able to identify what's going on between these two here. And that's a representation of the Heisenberg uncertainty principle. Now, this is my 1 or 2 minute discussion of the derivation of the uncertainty principle. It's actually, the reasoning behind it is really quite clever. So for waves, which as we know in quantum mechanics, everything is a wave. We're waves, we have just a really fast wavelength, a really small wavelength. In the case of some of the experiments that my group does, we do neutron scattering. So you take a neutron, which is a really little mass. If you cool that neutron down to around 3 to 5 Kelvin, it starts to behave like a wave with a wavelength on the order of maybe 3 to 5 angstroms. And so then you can scatter those neutrons just like you can X-rays. And so that's something my research group does for study. So we can take advantage of this wave-particle duality, even for, not even an electron, but something else has a significantly higher mass. So for waves, the momentum and the position are related through a Fourier transform. And momentum is another way to classify kind of the energy of the system. So if I have a system where I exactly know, this is the delta function, right? So we have a little delta function here. So if I exactly know the position of a particle, the Fourier transform into momentum space is 1. Right? So if I exactly know the position in real space, when I go to Fourier space and I want to know the distribution of energies or momentums, I have no information whatsoever. And this will hold true for any type of function that you'd like to have. Right? So if you take a Gaussian with a really narrow distribution, you'll get a Gaussian with a wider distribution. But the key thing to keep in mind is that the Heisenberg uncertainty principle is really just a direct application of if you treat particles as waves, then you have to have this relationship between your momentum of the wave versus your position of the wave. Right? So if you have a standing wave, for example, or particle in a box, all those different types of things. Okay. So let's move on to an actual example here. So let's look at particle in a box. So from quantum mechanics, so this example could be like a monatomic gas. Ideal monatomic gas. The energy from quantum mechanics as a function of 3 quantum numbers, Lx, Ly, Lz, is equal to, oops, no bar there, sorry. Planck's constant squared, 8mv to the 2/3. This is volume, this is mass. That's the volume of the box. And it's equal to Lx squared plus Ly squared. So we're not going to be relying too much on quantum mechanics, but we're going to use quantum mechanics to help us sort of on occasion. But we're not going to go through the solutions. We're just going to pull them right off the shelf. Let me get this out of the way a little bit. So epsilon here this epsilon is going to either represent the energy level, meaning that if I plug in a value for Lx, Ly, and Lz, the energy that I get out is going to be the energy of this particular microstate. The energy state is going to be the energy that's going to be a function of these individual parameters. And so we're going to take a look at this really quickly. So we're going to map out 3 energy states that are going to be a function of Lx, Ly, Lz. And this is going to be proportional to summation of Li squared, which is going to be a property of all the energy levels. So bear with me for 1 second here. So if I plug in numbers 1, 1, and 2, 1 squared plus 1 squared plus 2 squared is going to be equal to 6. So this is going to be kind of like a scaled form of the energy. This is the energy level. This is the energy state. We can repeat this process. 1, 2, 1 has the same energy level. 2, 1, 1 has the same energy level. So for the particle in a box, the E level, in this case of 6, is what we call 3-fold degenerate. And we denote this with a lowercase omega, meaning that there is 3 different ways that the system can organize such that it has the same energy level. As we'll get to over the next couple of days, what's going to end up happening is the energy of the system is going to be a combination of the energy level times by their degeneracy. So it's not going to necessarily be the highest energy or the lowest energy level. It's going to be the product of the probability of the number of different ways you can have a particular energy level and that energy level itself. So it's going to be a balance between those two effects, which you can kind of think of as energy versus entropy getting to your equilibrium configuration. Does that make sense? So I kind of ran out a little bit of space right here. Capital omega lowercase omega is going to be the degeneracy for a single particle. Capital omega is going to be the degeneracy for a collection of particles. So today is kind of more of a definition day, but we'll get into the meat of the calculations very shortly. Okay, so to clarify, an energy state is very discrete combinations of sort of quantum numbers or properties of the system. Energy level is just the energy of that particular state. But there can be multiple states that all have the same energy level. Same thing with having a collection of particles. There's again multiple states that all have the same energy level. So, we're going to write Nj so Nj is going to be the number of molecules, or particles rather, I should refer to them as particles more generally, in a particular state or energy state, and we're going to denote that with J in this circumstance. E of I is going to be this is going to be the total energy of a particular microstate, or call it the ith microstate. So if we want to know the total energy of a particular system, based on, in this case we're assuming non-interacting particles to make the mathematics much more simple. I have a collection of n particles. Some of those are going to be in a particular state. We're going to keep track of all the particles in all the different states. The total energy of the system, assuming non-interacting particles, is going to be for the I microstate. And of course, there can be lots and lots and lots of different microstates. So this is just one microstate with multiple different particles in the system. We're just going to keep track of how many particles are in a particular molecular level state, times it by the energy level of that state, add up all the particles in all their states, and this is one microstate. Then we have to do some more mathematics, which we'll talk about over the next couple of days. How do we translate between the energy of a particular microstate to the average energy of the system, which is what we would expect to measure macroscopically. Right? So the way that we can think about this is that the molecules are tumbling and going through microstates often and very, very quickly. If I sample it, what's the most probable sample I'm going to obtain? Based on the volume that I'm sampling, for example, like if I'm measuring the temperature, measuring the pressure, how much volume am I actually sampling? And are we going to get a statistical average of the system by sampling that volume over the course of time, over the course of that volume that we're sampling? So it's a little bit muddy right now, but we'll be using these terms a lot more such that hopefully it'll be a little bit more clear as time goes on. So that gets us to the cornerstone of StatMech. Two principles that are ones we have to believe are true, otherwise everything falls apart completely. Then I'll use these as examples to hopefully show some videos. So, these are the two most important StatMech postulates. We have to assume them, otherwise we cannot perform any calculations whatsoever. So number one is called the equal a priori probability principle. What this states is that if you have, there's a lot of conditionals here, but in general, if you have the same, if a microstate has the same energy, it is equally probable. Just abbreviated micro here. If microstates have same energy level, they are equally probable. Right? It's basically saying that the system only behaves with respect to the energy that it's given. Now, the book itself, this is the end of chapter 1, has these in a little bit more rigor. It says, if they have the same volume and the same number of particles, but for the most part, the catch of it is all, if the system has the same number of particles, the same volume, and the same energy, it's equally probable microstates. That's the key. So there's a lot of other conditionals, but the energy here is kind of the most important one, assuming that, of course, we're keeping everything else constant in the system. The second is the ergodic hypothesis. Has anyone ever heard of ergodicity or knows what the ergodic hypothesis or principle is? So I'll read it out, I'll write it here. So what the ergodic hypothesis states is that we can replace the time averaged property of a macrostate, meaning if I put a thermometer into a solution, right, that's a time averaged property measurement. It's averaging over the course of seconds or minutes in our life. I can replace that with the average of all microstates weighted by their probability of outcome. Okay, so what that means is that I can take a time average of a particular system and relate that exactly to a statistical average. Okay, so if I have two systems here, I have several boxes. Then I'm monitoring over time how the particles are moving around. Okay? Now I can imagine that I take every single one of these snapshots and I put them together into a box. Right? So what I'm doing is I'm sampling some system as a function of time, and I'm watching the particles move and progress. And if I sample it at times when the positions are uncorrelated to the previous time step, meaning that there's no history of how I initialize the simulation or initialize this process, I can essentially take each one of these individual boxes and then assume I'm putting them together to make an even bigger box. Now, if I sample this millions of times over again, I can make a box that's a million times bigger than my original box. This is in many ways what we're talking about when we say the ergodic hypothesis. So instead, I could also imagine, let's say you're on a homework problem and I say, how many different ways can you put yellow balls into green boxes without repeating and pulling out, right? That's classical statistical mechanics type calculation. Here's one snapshot, here's another snapshot, here's another snapshot, here's another snapshot. So in this case here, you're just coming up with all the different possible statistical configurations in the system. That's going to be exactly equivalent to breaking these apart and then building it off as a function of time. That's the ergodic hypothesis. And that is the link between two types of simulation approaches, molecular dynamics and Monte Carlo. And that's what I want to show a video of. Maybe like just, they're short videos, like a minute a piece, just long so. So molecular dynamics is like this system up here. Another type of simulation approach is called Monte Carlo, which we'll be talking about these in a little bit greater depth, but it helps to have an entry-level understanding of what these techniques mean. So it's a way to kind of, at least for me, it helps me visualize. So in molecular dynamics, I'm giving every particle a set of rules, how attractive they are, how repulsive they are, what velocities they have initially, what positions. Then I just integrate them. Imagine like planets rotating around each other, or a galaxy rotating, right? It's a similar like approach. But instead of gravity being the source of attraction, you have electrons being sources of electrostatic attraction and repulsion. Another way here is Monte Carlo. You don't actually move the molecules around following any set of rules. You just randomly grab a molecule and you randomly throw it some other place and say, does that lower my energy? And if it does, you say, boom, that's an acceptable configuration. Do that millions of times over again, and you develop sampling like this. So again, this is going to be a gamble here. If I can get this fired up and running in time really quickly. Let's go HDMI. I have some videos queued up on YouTube on my phone. I believe these are both water. They're just random ones I saw that kind of illustrated the concept that I wanted to. They're a little bit different, but I think they get the point across of what I'm trying to communicate here. And it gives us a way to really visualize what we're talking about. Let's see. Here we go. Here we go. So this one here, this is an ab initio simulation of water. So this is not exactly molecular dynamics. It is more or less. But instead in this one here, they're actually calculating the electron clouds and using that information. So this is actually a quantum mechanical calculation. The purple lines are just for illustration right there to highlight the different structure of water. But basically, this is a time-based sampling of a fluid property itself. And so you collect this information for a very long period of time. Every so many time steps, you use those snapshots to analyze the results. Then we can figure out what the density is, what the pressure is, what the chemical potential. We can get all the information we need from the system based on how these are kind of progressing through the system. So this is analogous to a molecular dynamics type simulation where you're just modeling and watching the particles rotate and tumble around. And this is how I tend to view a lot of what we're dealing with here, is it's sort of like a map perspective. Now the next one, let's see, is a Monte Carlo type simulation. So in this one here, the particles are jumping around randomly. Now this one here, I think they're initializing at a high temperature, and so they've contained all the molecules in a box, you can't see it. And then they start to shrink it and cool it down. But as you shrink it and start to cool it down, eventually some of these molecules really get trapped in sort of these local low energy wells that correspond to kind of a crystallization of ice. And this one here, they introduce a methane particle and see where the methane goes in. So you can see the ice is beginning to crystallize. I think this one here, they're dropping it down to a really low condition, like 1 degree Kelvin or something like that. So you can do whatever you want. Yeah, so it gradually approximates 1 Kelvin. And so you're getting is kind of the ground state configuration. But you'll notice that at the beginning, they were just flying around randomly, right? They were just willy-nilly moving particles around, and almost every interaction was accepted because the energy didn't get lowered. And we'll talk about the conditions for how you do these simulations overall. But this gives you an idea of a Monte Carlo simulation, which is more akin to what we'll be doing, but instead of using computers, we're going to be doing pen and paper, right? Instead of us sampling all the different configurations of the world and the universe, having a computer guess and check, right? When there's lots of configurations, we have to have a computer guess and check. We're going to be focusing on simple systems where we can actually come up with every single possible configuration of the system. For example, like a particle in a box, this is it. This is every single possible configuration that you could ever possibly have for a particle in a box. Lx, Ly, Lz. This goes to infinity. So in theory, there's nothing to stop a particle in a box from having an infinite energy. So there's some ways that we play around with that. If you have an infinite energy, there's an extremely low probability of being in that state. And that's what all kind of works out to be together. But what we're going to do, what this is doing here, we're going to be doing with pen and paper, or using other theories that have been developed that actually fully quantify all the different possible configuration spaces in the system. All right. That's our intro to StatMech. So no office hours tomorrow. Homework will be due at 5 on Wednesday, so you guys can have access to talk to Chinmay before it's due. And shoot me an email, and I'll try and respond, but it might not be until later in the evening tomorrow. Thanks.